Hi everyone, good day, good day. So today's lesson is going to be on Ka and Kb. So last class we looked at Kw. Now, what does this have to do with everything we've been talking about? Let's get right on to it. So Ka is known as the acid dissociation constant. Okay, all right. Dissociation, I understand. Acid, I understand. Maybe that's where the A comes from. So let's take a look at this reaction right here that we've been looking at for a while now. This is, of course, an illustration of what happens to a weak acid in aqueous condition, where it reacts with water to give you an H3O plus and A minus. We saw from last time that HA is an acid. It's a weak acid in this case because of this equilibrium sign. Because if this was a strong acid, it wouldn't have this sign. It would just have this sign. H2O becomes H3O by receiving the H from the acid. Makes him a proton acceptor. So H2O is acting like a base. Now, because this is a weak acid reaction, this reaction will, of course, go backwards. And in fact, it goes backward more often than it goes forward. H3O becomes H2O by donating a proton. This guy is a conjugate acid, which makes this, of course, the conjugate base because A will receive the H donated here to become this, conjugate base for short. We saw last class why this is the way it is because this conjugate base is a much stronger, much more effective proton acceptor than this base. Okay? H2O is not that good in terms of accepting H's than A minus. That's why the reaction predominantly points towards the left. Now, because this has an equilibrium sign, it should make sense that I show you an equilibrium expression, right? So Kc is equal to H3O plus times A minus over HA. I almost forgot the H times H2O. All right. So if you were to isolate H2O and Kc to one side, Kc times H2O will equal to H3O plus A minus over HA. Okay, this equation right here is an abbreviation of what we are talking about. That is Ka. The dissociation constant for whatever weak acid you are talking about. And we will, definitely we will elaborate this a whole lot more as we move along. So let's talk about Kb, its cousin. If Ka is the acid dissociation constant, of course Kb would be the base dissociation constant. And here's a base reaction, a Bronsted-Lowry base reaction. Look how nice it looks. As you can see from this reaction, this base right here, okay, is picking up an H, like what all bases do. Proton acceptor, right, becomes BH. H2O willingly giving up an H to this base is a proton donor, so H2O is acting like an acid. Same with going backwards. BH is going to donate the H to become B. So I'm a donor. A is a donor, which means this is a Ca and this is going to be a Cb. Why is this weak? It's because BH plus is a better proton donor than H2O being a proton donor. So if I'm better than you at donating proton, the reaction goes this way, which makes the base weak in nature. So same idea here. Kc is equal to BH plus times OH minus over B times H2O. Okay, isolating for Kc and H2O, that Kc times H2O is equal to BH plus times OH minus over B, which in fact is Kb. Okay, so there's your Kb expression for base. Now, I have a little note down there in bold and in italic that both Ka and Kb are actually constants for a specific acid and base. Oh, look at this. Looks like Adidas. Acid and base. Acid and base. I'll make sure this is corrected in your version at a certain temperature. Now, what that means is that Ka and Kb are temperature dependent, which you already know. You already know that. Because remember Le Chatelier principle? Remember Le Chatelier principle? That when temperature increases or decreases, it will affect the equilibrium positioning. If this thing were exothermic, okay? Exothermic, it gives off heat. If you were to increase the surrounding temperature, the reaction will go this way, which means Kb right here is going to be a lower number because you'll have a smaller concentration of products and a higher concentration of reactants, right? Now, if you lower the temperature, okay, this being exothermic, and you lower the surrounding temperature, well, the reverse will happen. Lowering the temperature will cause the reaction to proceed more that way. You'll be making more products if you decrease the temperature of an exothermic reaction, which means you're going to get a higher Kb. Why? Because there'll be more products versus reactants. So these Ka, Kb, Kw are all temperature dependent. And what you'll see later on when you're trying to search for Ka value, those values are based on SATP. Just like most of the value that you can pick up in our CRC handbook or the IB constant booklet. Okay? And because of that, because this is an indication of how much this is, we can say that Ka and Kb can actually tell us how strong an acid and base is. So, this is how you tell. The bigger this number, the stronger the acid or the base. Obviously, this is a Kb. If this number is big, the base is going to be strong. Or stronger. Still a weak base. Don't get me wrong. Still a weak base, but a stronger weak base. Okay? If this was a Ka value, and this Ka value is huge, it's going to be a stronger acid. Still a weak acid, but a stronger weak acid. So a lot of people, and what they do is that they turn this into a pKa and pKb. That way it kind of reminds them that the lower the number, the more acidic something is, and the higher the number, the more basic something is. So put that into a negative log value. Okay, so you'll see pKa, pKb, okay, sort of resemble pH. Anyway, problem time. Okay. In this question, I'm going to be calculating Ka, given what I have here. Okay, and what I have here is pH value of vinegar. And the concentration of this is 0.01, and I want to know what the Ka is. How do we do that? How do I find out what the Ka is given the concentration of your acid and its respective pH? Well, let's draw out the reaction here. This is what happens in aqueous condition, that when you react this with water, you get H3O plus and acetate ion. Okay? Pretty simple, you ask me. Now, it is an equilibrium reaction. So what that means that is there's an initial concentration, and the initial concentration for the acetic acid is 0.01 molarity. Now, water does not play a role because water is going to be incorporated into this value. Remember, the concentration of water is the product of the equilibrium constant, right? So by finding out what this is, you'll find out what this is. So this is quite irrelevant. But then in the beginning, initially, before you drop anything in water, you'll have nothing here and nothing here because you haven't dropped it in water yet, right? This guy is not going to dissociate and make this if I haven't done anything. But I will. I will eventually do something because that's what change is going to be all about. And that is based on the molar value. Okay, the coefficient here. And the coefficient here is 1. So that's minus 1x. Okay? Every minus 1x here, you will gain a 1x and a 1x due to their coefficient being 1s. And at equilibrium, we call this an ice table, and this is something that you already have seen, and you're like super good at this. At equilibrium, so when this reaction, when you actually drop this guy in water and partially dissociate, you're gonna get an equilibrium situation. And that situation is going to be the initial concentration minus whatever the change is for acetic acid. And for H plus, you started with nothing, so therefore at equilibrium, you're just going to gain whatever the change is. And same with the acetate, you're just going to gain whatever the change is. Okay? Usually what I do here is I write out the equilibrium expression. And the expression here is that Ka is equal to x times x over 0.01 minus x. So that's what the expression is. This x right here represents H3O. This x right here represents at equilibrium acetate. Of course, this mess is at equilibrium whatever to acetic acid. Okay? However, in this question, we are obviously calculating what this is. Which means we're going to have to find out what these are. Is there another clue to find out at equilibrium, what is the concentration of H3O? Is there a clue? Is there a clue? Is there a clue? Concentration of H3O. Hey, wait a minute. Isn't that what pH is? pH is really just the negative log base 10 of concentration of H plus or H3O. If I were to reverse this to get rid of the P and just be H plus, that's this number right there. That's this number. Let's do that right now. So if pH is equal to 3.38, okay, H plus is nothing more than 10 to the power of negative 3.38. That is 4.17 times 10 to the power of negative 4. I hope I'm right. Okay, so that is X. Oh, nice. All right, so let's plug that number in. So 4.17 times 10 to the power of negative 4 times 4.17 times 10 to the power of negative 4. Divide that by 0.01 minus 4.17 times 10 to the power of negative 4. Now, when you're punching this into a calculator, I guess it's very important that you put those brackets just to make things organized. This will give you Ka, and Ka will be 1.8 times 10 to the power of negative 5. Okay, that is the acidic dissociation value constant of vinegar. We'll take a look at this. Okay, what you might want to do is maybe check my calculation. Hopefully I didn't make a mistake. You know I'm notorious in making mistakes, right? All right, let's do part B. Part B says, calculate the percent dissociation of acetic acid. So you started with that. Okay? And you'll notice, of course, you have that. What is the dissociation constant? How much H plus are you going to make is how much it will dissociate, right? Because if you remember correctly, HA dissociate to give you H plus and A minus. Okay, we know that this is a weak acid, but we know for sure this is not going to be 100%. So what is it? What is the percent? How much of this are you going to make for every one of these? This is nothing more than a simple division, isn't it? How much of these are you getting per how many of these? Oh, times 100, of course. And that's simple because we know what this value is. We know what this value is. So let's plug that in. So that's obviously 4.17 times 10 to the power of negative 4, okay, over 0.01 times 100, and the answer here is 4.17%. Okay. Again, okay, you might want to check to see if my answer is correct. Okay, they always say that I make mistakes all the time, and that's actually the truth. I do. All right, that's how you find dissociation percentage. So before we continue, let's take a look at this number. So acetic acid, okay, if you're looking at 0.01 molarity of it, that is worth this pH. By knowing this, we were able to discover what the Ka is by doing this calculation. Well, remember what I said. If you're doing this at room temperature, and maybe I am here, maybe this is SATP, which is really 25 degrees Celsius. If I'm doing this gives me this. I'm gonna put it in a database where people can just look and find out. Here's the database. Okay? This is something that you'll find on a CRC handbook. You can find it in many textbooks, grade 12 chemistry textbook, university textbook, the IB constant booklet. You can find these information. Here's acetic acid. At SATP, this is the dissociation constant. Whoa, we're pretty good. Look at that. Look at this. Look at this. Look at this. Look at this. We were right. And I didn't grab these numbers out of nowhere, by the way. These numbers, I actually prepared 0.01 molarity of acetic acid. And I took a pH meter. And I measured that, it's 3.38. And obviously I'm doing this at room temperature. Okay? So, hey, very good, very good. And of course, there's other acids. These are all weak acids like benzoic acid that you will learn later when we do organic chemistry, nitrous acid. Okay, and a lot of these are organic acids. You say, look at this. Look at these are all organic acids. So organic acids are all weak acids. Citrus acid. Okay, vinegar is actually an organic acid. Acetic acid is an organic acid. Okay, there's other acids like fatty acids. Hey, you know, biologists out there, fatty acids, that's a weak acid. And then we have Kb value, which is the base dissociation constants for a certain amount of base, certain type of base. Look at this. Ammonia, remember? We always have him as the representative for Bronsted base. And, you know, he has his own Kb value. Okay. Remember, for every Bronsted base, there's a respective conjugate acid. NH3 is a base. He has a conjugate acid of NH4+. If I know what Kb is, guess what? I know what the Ka is for this guy. You don't really have to look up. You don't have to go and say, oh, where is NH4? Because I know that NH4 is an acid. Is a conjugate acid of a weak base. Is there a Ka value for NH4? There might not be. You may be looking at those CRC handbook and you may be, I can't find ammonium. I can't find ammonium. That's okay. As long as you can find ammonia. You can find ammonium's Ka. And that is based on this equation right here, because we know what this is. That's 1.0 times 10 to the power of negative 14. And as long as we know what this is, we know its respective conjugate acid. So if somebody were to ask you, hey, what is the Ka for this guy at SATP? You just have to find Kb, apply this formula, and you'll find Ka of its conjugate counterpart. Let's do example 2. Okay, example 2 is based on, again, calculate Ka. Okay, for hydrofluoric acid, if 0.1 molarity of this at equilibrium has a dissociation constant of 7.8. Now, this is a little different from question 1. Question 1, I gave you pH. I pretty much gave you the concentration of H at equilibrium. This time, I did not give you the concentration of H in equilibrium, but what I did give you is the change, if you think about it, the change, the dissociation percentage. Isn't this the change? All right, let's do this question. HF is a weak acid. Hydrofluoric acid is a weak acid. It actually reacts with water to give you H3O plus and F minus. Okay, So it deserves a nice table. It certainly does, because we are starting with 0.1 of these. See? And we had none of these, none of this to begin with, because we haven't dropped this in yet. Jeez. The ratio is 1 to 1 to 1 to 1. So you can pretty much bet that you'll start losing some HF, while on this side you start gaining some H3O, you start gaining some F minus. How much? It kind of tells you how much, isn't it? It tells you how much. Meaning for every one of these, 7.8 of them will turn to this. You get it? So let's say there's 100 of these. You'll get 7.8 of these every time this dissociate. That's a big clue. 0.1 minus x. This is x. This is x. Again, I want to find out what is Ka. Now, as I said, this is pretty simple if you think about it. Okay? Pretty simple. Because we know what x is, because we already know what the dissociation of it is going to be. Okay? And that is 7.8%. That is 0.078. Gonna have to change that to a decimal, you know. So what that is really negative 0.078. This is really plus 0.078 plus 0.078. Huh, look at that. 0.1 minus 0.078. Okay, so let's put this in. Okay. That way we know what Ka is. Ka is going to be over okay, so using my super fast math skill, call a calculator, Ka is going to be 6.6 times 10 to the power of negative 4. So that's the dissociation constant for hydrofluoric acid. Okay. So if they give you the dissociation percentage, don't be afraid to just use the theory and say, oh yeah, the percentage. This is, you know, really the amount of H plus over the original concentration of the acid times 100. Well, if this is really H plus, this is really just a change. All right. So hopefully you guys are okay with that. I mean, it's really not that hard or anything, but let's move on to the next question. Okay, problem number 3. I think I made it. Did I make an error here? For some reason I keep thinking, oh yeah, you know what? I think I made an error here. I made a bad error. But I still got the same number because I know the answer. 7.8 divided by a no wait. I think I must have missed a step here. Okay, I think I missed a step here. This is quite embarrassing in terms of why I chose X to be 0.078. It's not 0.078. Sorry. X. No wonder it looks weird. These are not 0.07. What a waste of memory if you think about it, because all these video has memory involved. You can't just directly put this number, okay, as a change, because it's not. This is not the change. This is the change respective to this. Oh my goodness. This 7.8 is respected to this. What that means is that before you turn it into x, you have to take this with respect to, well, first you divide that by 100, so that's 0.078, and you have to multiply this by 0.1. You have to multiply it by 0.1 because this percentage right here is not just a change. Oh my goodness, this is not just a change. This is the change respective to the original concentration. No wonder the number looks weird. That is x. Huh. So let's plug that back in. Okay, so your Ka should be this. And because I know the answer, because I worked out this beforehand, just forgot about that, this is still 6.6 times 10 to the power negative 4. Because if you're wondering, if you're punching this in and you're like, how come I didn't get 6.6 times 10 to the power negative 4? Well, that's because I forgot to show you this, and I just put that in, and that's obviously wrong. Okay, so don't make the same mistake I made. I am so sorry. Maybe I did this purposely, just to show you what you should be careful about. All right, now let's go to problem 3 for real now. Okay, problem 3. Calculate the H plus concentration for acetic acid of this concentration. Oh, and calculate pH as well. Well, if you have this, you just negative log this and you'll get this. So here we go. Okay, CH3COOH is a weak acid. So what that means is that there's going to be an equilibrium sign of H3O plus and acetate anion. Let's do a little ice table, and we started out with 0.1 of these. None of these. This will decrease. These will increase, and this is obviously something that we are very interested in. And at equilibrium, 0.1 minus x. These are x. Okay, and my job is to find out what this number is and then negative log that to get the pH. So I need to write my Ka expression at equilibrium. So Ka is equal to x times x, so that's x squared, over 0.1 minus x. And I want to find x. And you're probably thinking, what's Ka? Well, I guess if I didn't say, we would assume that this reaction is under standard condition. So if you can go back to this, there's your Ka. Feel free to use it. So that's 1.8 times 10 to the power of negative 5. That's equal to x squared over 0.1 minus x. Now remember, when we were looking at equilibrium, we had a little rule called 100 rule, that if you take the initial concentration and you divide that by the equilibrium expression, and if that number is greater than 100, you can make an assumption like this. 0.1 minus x is sort of just 0.1. Because this number is going to be a very, very small number. So if you take this and you divide it by this, and if that is over 100, you can make this assumption. Because this assumption is very important mathematically. It saves you lots of minutes of work. And I can tell you right now, it is. Okay? So because of that, we can easily find x to be, okay, let's see what my calculator said. Okay, times 0.1, root that, and that is 0.0013. See how small x is? So if you take 0.1 minus this number, it's really still 0.1. It's almost like $100,000 minus $1. You really still have $100,000. Okay, so there we go. This is your H3O. You want to know what the pH is? It's very simple. Just negative log that. Okay, so by negative logging 0.0013, your answer is 2.89. Okay, so vinegar at standard temperature and pressure has this pH at this concentration. Okay, all right, here's another question. This one deals with nitrous acid, so make sure you go back and find out what the Ka for that is. You guys can work, you can do this on your own. I worked this out already ahead of time, and the answer for this is 9.9. Is it nitrous acid? No, it's not. Yeah, it's not. Never mind. I'm not going to give you the answer for this. Oh yeah. Yeah. pH here is 1.74. Okay, that's the answer. I'm just going to give it to you. Or are you guys going to be asking me, did I do this right? And maybe we'll take it up next class. Who knows? So the answer here is 1.74. Okay? See if you guys can get that. I hope I'm right. All right. Next question. I guess we can just finish off with this question, and I'll give you the next one to do, and then we'll call it. Okay? So calculate the pH of 0.56 molarity of ammonia. Okay, there's my ammonia. If I were to react this with water, I will get ammonium plus OH. Okay, it's a base. So there's my ice table. This is a base one. So I have 0.56 molarity of this. None of these. So this is going to drop. These are going to gain as I immerse NH3 in water. So at equilibrium, these are my respective numbers. The one that I'm interested in, of course, is this. Or this is really the same number, okay? Because this tells me the concentration of OH at equilibrium. If I take negative log that will give me POH. Right? If I subtract that by 14, that will give me my pH. Or the other way around that I've shown you last class. Okay, if you get the concentration of OH, all you have to do is take KW and divide it by OH. Same thing. You actually get the same thing. All right. Since this is a base, you're not going to go find Ka, are ya? No, you're going to find Kb. So Kb is equal to x times x over 0.56 minus x. Okay? And let's take a look at what ammonia is. So ammonia is this number right here. So 1.76. Okay. 1.76 times 10 to the power of negative 5 is equal to x squared over 0.56 minus x. Again, let's check to see if I can use the 100 rule. Everybody, pray the fact that we can. Because if we can, that will save us a whole lot of work. And yes, we can. Because 0.56 divided by KB is like 31,000. That's x is a tiny, tiny number. Okay, so x is equal to 1.76 times 10 to the power of negative 5 times 0.56, and then we root that. X is 0.0031. Yep, it is a very small number, at least compared to 0.56. So that's the concentration of OH. Okay, but that's not what we want. We want pH, so that means we're gonna find the pOH, and that's negative log of 0.0031. So what would that be? That's gonna be 2.51. pH is gonna be 14 minus 2.51. That will be 0.11.49. Definitely a number representing a weak base. All right, this one's yours. Let me just tell you the answer. The answer is 9.94. Okay. That's again, a weak base number. Don't go find KB for this. I'm going to give you KB for this. This is not something that you can easily find. I researched this, and it is 7.5 times 10 to the power of negative 7. This is the KB value of this thing called morphine. It's a painkiller. Very powerful painkiller. I think they use this for people who are GG with cancer. Okay, when they're on the deathbed, and make them feel better so they're not in so much pain. All right, hopefully I'm right and you got this. We'll take it up next class then. Bye.